డ్రైనేజ్ మెకానిజం ఇవన్నీ కూడా చేస్తా ఉన్నారు. దట్ ఇస్ కాల్డ్ స్మార్ట్ సిటీ అన్నారు.
So, good afternoon, dear participants. So, today morning is the fourth day, fifth day. Today morning we had an industrial visit to the PV power plant of Triplex Soaps, and today afternoon we are fortunate to have Mr. K. Balakrishna sir from the electronics. He's senior management position, and he's having experience in DC-DC converters, electrical vehicles, and telecommunication, railway projects, and all. So I heartily welcome sir to give a session on the today afternoon. Please welcome sir. HOD Madam K. Rajni Madam inviting sir with a bouquet.
Let's come front.
ముందుకు రండి అమ్మ, ముందుకు రండి.
Come front.
Yeah, good afternoon. So today we learn something about. See, this is not a seminar or something. This is just a informal class. Okay, we'll just learn about a DC-DC converter. So all of you are from electrical background or
Electrical background.
electrical background, and you are in second year, right? Okay. And I hope you are aware of the basics of semiconductors, right? Understand how a transistor works, how a diode works, etc. Okay. So what's a DC-DC converter? Have you all heard about a rectifier? Yeah, what it does? It converts what it does? Converts AC to DC, a rectifier. So basically, you have a sinusoidal AC, okay, which is going in bidirectional. So it is going from positive VP to negative VP. All the AC voltage will be in a sinusoidal form. It will be oscillating from a plus VP to minus VP. What a rectifier does is, instead of having a bidirectional thing, it will goes into a unidirectional thing. So it will be always transiting from 0 to plus V and then 0 then plus V. So basically what a DC-DC converter does is, so it will be converting the voltage from one level to another level. Say if it is from 10, it will be converting to a less than 10 or a greater than 10. But it will be of the, it is a basically a converter, okay. So it is, it will convert a voltage of DC to another level, but the properties are, it will be ensuring a stable output. Stable in the sense it's a regulated output, and then it does in a very efficient way. Okay, so that is what a DC-DC converter does. So why do we need a DC-DC? So I'll share my industrial experience. Okay, so basically I work for a railway product development company. So we had one. Are you comfortable in English or you want in Telugu? Telugulo చెప్పాలా English పర్వాలేదు? English is okay? Okay, fine. So there we had to develop a product, okay? It was something a railway data logger, okay, which will be placed along the tracks. So it's somewhere in a remote location. So there the power supply available to power my data logger was 110 volts DC, okay? This was something in way back in something around must be 1990 or something, okay? So what we had to do was we just used a linear regulator, okay? So we used a linear regulator. Then we had a 110 volts which was made of about 12 volt batteries. So what we have done is we have tapped the output from one battery, so which gives us 12 volts, and then we try to regulate it for using a reference to get a 5 volts output to drive my data logger. Okay. So my data logger was taking something around 1.2 amps. The issue with my power supply was, so there was a 7 volts drop across my series pass segment. So that it is giving me around 8. It is there. Actually, I am using how much? I am using a 5 into this. I am using a output wattage of 6 watt. And then since I was using a 12 volt supply, I had to drop 7 volts across my series pass element. So the net input wattage what I was consuming was 14.4 watt. So I was wasting around 58.3% of my input power supply. So what is happening is, it's for 47 for 66 watt output, I am using a 14 watt input. So which is very, I mean it's not efficient, okay. And the other part is, for this thing it is dissipating around how much? 7 into 1, around 8.2 watt of heat. So it was dissipating as 8.2 watt of heat continuously. So to dissipate this heat, we had to put a big heat sink. Heat sink is the aluminum profile we use to absorb the heat from the semiconductor and dissipate it to the environment. So what happened was, due to this heat, and this particular thing was supposed to operate 24 by 7. So that once you switch it on, you cannot switch it off. It will be on for 24 by 7 continuously. So continuously I mean 8.8 watt of heat was generated, because of which this, as what happens when the ambient temperature or when the temperature on a semiconductor increases, what happens? Its performance will come down. So due to this heat, my performance was coming down, and fortunately that particular regulator was having a thermal shutdown, so power supply was switching off. So there was no problem with my data logger, no problem with the power supply, but because of this heat, what is happening? The entire equipment was off. This was the condition when this DC converters were not available. So you had only linear things, and linear things used to dissipate heat or base. So what has happened? The excess energy that is required was always dissipated as heat. So instead of doing that, for a continuous increase in efficiency, so instead of dissipating this as heat, you can store this energy. Okay, the alternate thing was you can store this energy. How do you store this energy? How can you store energy? Basically, in electrical, this thing you have two types of storages. One is you can store energy in an inductor. If you store energy in an inductor, you will be storing it in the form of magnetic energy. If you store it in the capacitor, you will be storing it as a form of electrical energy. So you can use these two elements to store energy, and then use a switching converter or the switching device to use this energy to power the load in a regulated form. Okay, so this is what is your DC-DC converter. So let's see how the DC-DC converter works. Here, for the clarity's sake, I am using a flyback converter. Okay, here the energy storage happens in a magnetic field, and that magnetic field is nothing but your transformer over. Okay, it's storing energy in the transformer. Okay, so this is a controller. Okay, you have a controller, you have a transformer. This controller will switch this transformer on and off. You have the input DC supply. Okay, and this is the output output rectifier, and then they get a output supply. Okay, this output supply is sampled through a feedback network where we have a V reference. Okay, V reference is based on the output I require. I use the standard reference voltage. Okay, this is the basic circuit, and this is the control winding that is going to power the control circuit of this control switcher. Okay, so this is basically the circuit. So initially when you switch on the power, what happens is this controller will switch at a frequency that is set by this controller. Say each switching circuit will have a oscillation frequency. Okay, so basically that oscillation frequency will depend upon the circuit you use. Let's say this is 100 hertz. Okay, 100 kilohertz. Sorry. Okay, so what happens is this will have intelligence. So to start with certain fixed frequency. Okay, so it might be switching at 100 kilohertz and a duty cycle of 50%. Like full duty cycle is 50%. Okay, so the total on time is 50%. So at the time, what happens is the voltage will start building up. It will be checking this voltage. Okay, whether through this circuit, to the feedback circuit, it will be checking whether the output is set to the required output or not. If it is not set, again what will happen? It will increase the duty cycle. Okay, it will keep on increasing and then checking, keep on increasing and then checking. Once this reaches the set voltage, say if I set this at 12 volts, if my feedback circuit senses that there is a 12 volts, how does it sense? I will be using a 12 volts difference, that is the 12 volt zener I use. So once my output voltage gets to 12, so till that 12 it keeps on increasing, okay. Once it reaches 12, what happens is the zener diode will break down. So once it breaks down, what happens is this is basically an optocoupler. So this is the photodiode or a LED. This LED will start emptying light once the output voltage exceeds 12. Okay, 12 is in the sense I've set it for 12. So once this exceeds, so this will emit light which is sensed by this phototransistor, and then through the control circuit, what happens is there will be some current flowing into this C pin. So the current is set by the induction of this feedback winding. Okay, so once there is a flow in this, there will be a program control within this controller. If there is a flow in this, there is current flow in this C pin, control pin, what will happen immediately? The duty cycle of this thing is going to decrease. Like say the on time is going to decrease. So the moment this on time is going to decrease, then internally there will be a MOSFET which is switching this inductor. So when when the on time is decreased, what happens is this will start the voltage build up at this primary winding will be getting down. So sorry, secondary winding will come down. So again it will come down till what time this goes off. Okay, in case it is increased, when it is less than reference, then again this will turn off. Then what happens? There is no flow of current. So what the controller does is, since there is no control current, again the duty cycle increases. This will be happening at a high frequency. That is, this control loop will be working at a very high bandwidth. So it will keep on sensing, and what the end result is, we get a constant output. Okay, this is how the DC-DC conversion works. Okay, this is the basic flyback conversion. There are other types of conversion which are similar. Okay, so what happens is this will be tracking this reference will be tracking the set voltage, and then based on this controller it will be changing the on and off time to maintain the output constant. This is how the DC-DC converter works. Okay, here just sorry to interrupt you, Advaita, because all the concept is around this. Okay, now let's come back to whatever you have learned, I think this year or previous year. Okay, so this is basically a bridge rectifier. Okay, this is a step down transformer and the bridge rectifier, and then you have a capacitor filter which is going to give you DC voltage across the load, right? Okay, so this is the rectifier. Okay, so this is a full wave bridge rectifier. So you get a rectified AC voltage, and then when the rectified AC voltage is applied across the capacitor filter, okay. Now if you see the current in this current that is charging this capacitor. So how much is this? It's a 50 hertz because all our mains voltage is 50 hertz. Okay. So what happens? How many milliseconds is one cycle? It's 50 hertz, so 20 milliseconds. So half is 10 milliseconds. So in this 10 millisecond, so this is 5 millisecond, this is 5 millisecond. So initially when you say the voltage starts to build up from 0, okay, what happens is, see till certain VF, okay. See this, the diodes will be having certain, forward voltage. So till the bridge exceeds the forward voltage of the two diodes, it doesn't conduct. So it doesn't conduct. So till 1.2 volts, it doesn't conduct. So from there on, it will start charging the capacitor. As the voltage builds up, the capacitor current builds up. Okay, and then once when it reaches this peak, its voltage is falling. So what happens? The capacitor will start discharging. So it no longer charges no longer draws the input from the current from the input. So there is the current rises. The current discharges the capacitor. So it falls down again. As the voltage is decreasing, the current falls down. So here in this 10 millisecond cycle, how much is the time that the capacitor is getting to charge? So till that it reaches, it exceeds the voltage exceeds that 2 VF, the forward cutting voltages of the two diodes. You don't have any voltage across the capacitors. So what happens is in this 10 millisecond, hardly there will be 3 milliseconds time where a capacitor gets charged. So what happens in your normal rectifier among the 50 millisecond cycle, okay, among the 20 millisecond cycle, sorry. So you have only 6 milliseconds that is charging the capacitor. Other 14 milliseconds, whatever is the stored energy in the capacitor, that should be powering the load. So to do that, you need a very high value of capacitance. Okay, you need a very high value of storage, which is not efficient. Okay, instead, what you can do, because this is the line frequency, you cannot do anything. So what you can do? The other alternative what you have is, why don't I change the time of this cycle? Okay? So how can I change the time of the cycle? So if this is a fixed frequency because I am taking it from the line. Instead, if I make this, if I can control this frequency, so I can reduce the time. Okay, instead of making it say 10 millisecond, must be I can make a 1 millisecond. Okay, in that 1 millisecond again, the time that is required for the capacitor to power the load is going to reduce. This is the principle. That's why we use in the switch mode power supplies. What we do is we switch this at a very high frequency so that the time required to charge and discharge the capacitor substantially reduces. So when the time reduces, what happens is the value of capacitance can be lower. Okay, so the higher the frequency, the amount of capacitance that is required to charge is going to be smaller, and then since the time required to, give power to the load also is directly, is increasing. So what happens is your size of the capacitor decreases and the charging interval also decreases. Thereby what happens is you can get a much efficient and a better regulated supply. So that's why what happens is you select a, whenever in a DC-DC converter, it is going to be a high frequency switching, not a low frequency switching. So in high frequency switching, earlier somewhere to start with, in the earlier first phase of DC-DC converters, this switching was around 32 kilohertz or something. But for this to, for this switching frequency to work, earlier all these transformers were what iron core, or we can say CRNGO. It is a steel core. So steel core never supported these higher frequencies. So what has happened was the next generation of the transformers were these ferrite core transformers, where they support higher frequencies. With the high gain magnetics that is available, now you can have transformers which can switch at even up to 1 megahertz. Okay. So as the frequency is increasing, what happens is the size of the energy required to power the load or store the electric field in the capacitor reduces. Hereby what happens is the size of the converter reduces. And other way is, if you increase the switching frequency, the square wave and sine wave get approximated almost. Right? There is no physical difference between a sine and a square wave as the frequency increases. Your sine wave and the square wave becomes almost similar. That is what we call a quasi wave. Okay? So that's why in a DC-DC converter, the first and fundamental property in a DC-DC converter is it will always be switching at a high frequency. Okay, as I told you, what are the basic differences between a, now we know that whenever you have a DC-DC converter, it is basically a switching converter. In a linear converter, it is only what it does is, beyond the reference voltage, what it does is it always dissipates the excess amount of, beyond the reference level, it will dissipating all the excess energy in the form of heat, which is wasted. Whereas in a switching converter, what we are storing that energy and then powering the load, so no dissipation happens. So let's see what are the difference between whatever we are saying a switching regulator is always also same as linear converter and a switch mode converter. Okay. So here, operating principle wise, this voltage regulation is via dissipation. So whatever is beyond reference, it is all dissipated as heat. And then the other one is, it is by switching. So what we do is we switch on and off to control the energy that is stored in the magnetic field of the capacitor. Okay. Then the efficiency, this is low. That will be even you get as of today you get DC-DC converters which are around 95% efficient. So heat dissipation, there is will be high heat dissipation. The other one is low, minimal because it's only switching. Okay, and then this uses a less number of components where there you need a controller and you require a inductor and a capacitor, etc. Whereas it is basically the component complexity is limited to a filter and a bridge rectifier. Okay, then size is this is here actually the semiconductor sizes are small in linear, but the heat dissipation devices like that is the heat sinks and all are very big. Okay, so it is in switching there will be a lot of harmonics, whereas in linear the amount of harmonics because it's switching at a lower frequency, the amount of harmonics will be less. Cost wise this is lower cost and this is a higher cost, but this higher cost will be concentrated by the efficiency. So this is a higher efficiency, the cost is compensated. So this is how the so in this DC-DC converters you have different types. Okay, based on the way you use your the purpose what it is you have a buck converter. Basically a buck converter is a step down converter. So from higher voltage to a lower voltage you convert that into, you step it down, that's called a buck converter. Suppose your input is always less than your output, then the converter is going to boost the output, there it is going to be boost. Sometimes you have a situation where your input is fluctuating from a high to a low, and but you require a constant output voltage. There you will be using a buck boost converter. Okay, and in buck boost converter, always your output is the invert of the input. So you get the opposite polarity. Again, you need to invert it, use it in a non-inverting cell. There, that's compensated by a inverting buck boost. So once you get an invert, again you invert it, you get a normal one. Then you have a step converter, which is a two-stage of buck boost for a high voltages. You use this. Okay. Here, till the earlier one, what we were telling buck boost and all thing is, there is always a physical connectivity between the input and output. Like say input and suppose you take a uh, take a multimeter and then try to measure the resistance between the input ground and output ground, it will show a short. Okay, meaning that whatever is your output circuit is there, the load reference is connected to the source reference. Okay, in certain applications you don't want that reference to be connected to the source reference. Okay, you want your output to be isolated from the input. In such cases you need a isolated topologies, like input supply is isolated from the output supply. So there you use a isolated type of converters. Okay, that means the input ground and output ground are not connected, they are separate. So there you have a flyback converter, as I explained in the earlier one. There's a flyback converter where, based on the turns ratio of the flyback inductor, there will be input output voltage can be varied. Okay, there is a forward converter. Okay, here there is the energy stored in the transformer, whereas in a forward converter you have a you have an energy storage inductor, you have a choke in which the energy is stored. That energy is converted by the converter. So that is the forward converter. So flyback converter is limited to the wattage. So it can only give you output till certain minimum wattages like few hundreds of watts. But anything beyond 100 watts, use a forward converter for isolated topologies. Then you have half bridge. Then you have push pull. Then you have bidirectional converters. These converters are based on the wattages. You have a different topologies that are present. Okay. So here all these topologies is the way you connect your storage element and the way you connect your switching element. It will the capacity output capacity changes, and then based on that this will your output will be available. So what are the applications where all these are used? Okay. So in these find extensive use in almost every electronic equipment that's available. So now, I mean, you can see for yourself, there is a self-explanatory thing. It is used in aircrafts because aircraft generates a single source of energy, and then different systems require different voltages. Where these DC-DC converters will always convert those voltages to the required voltages based on the end device. So similarly, you have on ships, you have on DC distribution microgrids, you have this we'll see at a later stage. So this is based on different requirements. You have different capacities of DC-DC converters. Okay. So what is the performance criteria? Okay. So whenever you have a DC-DC converter, how do you compare two DC-DC converters? Which is good, which is bad? First thing is the efficiency. So giving a required output, how much input is being taken by the DC-DC converter? That is the first benchmark for the efficiency. The second is form factor, is in the sense the dimensions. Okay, how small is my DC-DC converter? The third one is the reliability. So how good it works under various conditions like excessive temperature or excessive input or less input. Then ultimately the cost. These four are the performance criteria for any DC-DC converter. Okay. Actually, see, I was given the information that this was for a faculty who is, who is teaching you all these concepts. So, this was prepared in context that you are aware of what DC-DC converter and all your switching technologies is concerned. That's why I didn't, prepare this for people who are not, knowing the basics of what the technology of DC-DC conversion. Okay. So if it was for your learning type, I wouldn't have done this. This would have been a separate thing. But anyhow, let's see. Say DC-DC converter is basically a product. Okay. Like say your mobile. So when you go to a shop, you want to buy a mobile. So what will you say? Yeah, you require certain specifications like say your memory and your display type, and then what the technology, the transmission technology it supports, like the 3G, 4G, 5G, and then what all the camera resolution and all. Similar way, the DC-DC converter also has a specifications. Okay, for each application, they'll be having certain specifications. Okay, first thing will be the input specification. Okay, so the input specification will be the first thing will be the input voltage range. This is nothing but there will be some voltage beyond between which the DC-DC converter will be delivering the required output. Like say I want a 5 volts DC-DC converter, like here it is given. Okay, this is an example. Okay, so it is going to take 9 to 36 volts as input, and it will be delivering a constant output of 5 volts. So generally, in these DC-DC converters, the ratio will be there. So this is 1:4. So the minimum is 1, and then the maximum is 4 times the minimum input or the nominal input. So this is 1:4. Like that, you have 1:2. Like you have got 1:10. So based on different applications, this range is there. So what is the voltage range? It is for that range wherein the DC-DC converter is going to deliver us the required fixed output. Then the surge voltage. Surge voltage is unwanted voltage on the input. Suppose by certain chances there is a disturbance that is there. It is going to survive a disturbance of 50 volts, even though it is going to operate with 36. It is going to survive anything 50 volts for a 100 milliseconds duration. In case of any abnormality, this is going to survive 100 milliseconds. And then the input filter. So whenever we have a DC sources, what we need, whenever we have a power sources, first thing is what we do is, there are two types of couplings we require to provide. As a user, one is the power supply decoupling, what we call, that is done through a storage capacitor, and the noise decoupling, that is done with a high frequency capacitor. So generally across any digital device or analog chip, you have two types of devices that is connected across the power supply, that is VCC and ground pin. One is the storage capacitor, other one is the noise filtering capacitor. Generally, is going to be a ceramic filter. Okay. So this is going to be a pi-type filter that you have to connect it. And then have protection, which you have to provide a fuse. Okay, then in fuse there are two types of fuses. One is the fast blow fuse, other one is the slow blow fuse. So here this recommends a delay type means it's a slow blow fuse. Fast blow fuses are very sensitive, even the moment there is any inrush, it will open up. So which is not recommended in power supplies. You have got a delay type, that is a slow blow fuse. Internal power dissipation is like see here we have got a control circuit, okay. So it is this control circuit will take power from this input and then start functioning. So how much power that this internal control circuit consumes is called as the internal dissipation. That is generally going to be very low. So it's going to be 500 milliwatt. It's few milliamps that will be there. Nowadays, the benchmark in the industry is this power supply will be instead of internal circuits consuming milliamps, now the internal consumption is around picoamps. So it is going to be instead of milliwatt, it is going to be microwatts. Okay. Then the startup time. So the time that is required to attain to the maximum, that is the specified input, is going to be 30 milliseconds. So those are all the input. The similar way you have got the output. So what is that voltage tolerance in the sense? It is the variation. Like say if my output is 5 volts, then how much variation? So it is 1%. So something like 4.95 to it will be other one is 5.05. So it can vary from that. The rated power is what is that specified output current that it gives you and the output power it can deliver. Then ripple, ripple and noise. This is 75 millivolt peak to peak. Okay. I think you understand this ripple and this thing. I need not tell. The line regulation is see when the input is see we are telling that input can vary between 9 to 36. When this input is varying, what is the percentage of change in the output? That is going to be around 0.2%. Then the load regulation is what is the change of input between full load to no load condition. Here again you can see the switching frequency, typical switching frequency is around 400 kilohertz. It is going to be a high frequency this thing. And then these are all the functional controls. Like you have got a remote control pin through which you can give a TTL signal to it. It will be switching on and off. Here it has to be to make it switched on. It has to be like a this pin has to be grounded. If it is left open, it will be in off condition. Okay. And the other one is the environment. It will be having certain specified operating temperatures. So it can work from minus 40 to plus 80 degrees. And then for the worst, this thing case temperature rises, it is going to give you 110 degrees centigrade max. Suppose say, since this is a 40 watt converter, so there will be a temperature rise on that this thing. So to control this, so what will be the general acceptance range for any device? Suppose the room temperature is what? General standard room temperature condition is what? Yeah, 25 degrees. So generally if you place any equipment in this 25 degrees centigrade, what is the tolerable temperature that is accepted on any device? Let's say your laptop or your mobile or whatever it is. Can you guess? Hmm? You mean to say it can heat up to 40 degrees or above room temperature is 40 degrees? Hmm? Generally it is say whenever you have any device, the temperature rise, the acceptable temperature rise above ambient, that is if the room temperature is 24, it is generally allowed is another plus 10 degrees. So anything that has to, I mean that works normal in the sense it has to be 24 plus 10 is 34. Nowadays because of the certain other electronic reliability, it has become instead of 10 degrees, it has become 15 degrees. Okay. So if it is 24, again another 15, it becomes around 40 degrees. Anything beyond 40 degree, you have to provide a method of cooling. Like it can be I mean natural cooling in the sense you don't provide any cooling. It's called the mechanism is called natural cooling. Then if you have to have any, I mean external means of cooling, that is called forced cooling. You can use a fan or you can use a big metallic area to dissipate it. That metallic area will be called as a heat sink. Okay? So here you need to provide a heat sink in case that when you exceed a certain wattage where the case temperature is increasing. Okay? Then you have the humidity, then the storage temperature where you can store it. Why this is important is generally see if the devices don't have high storage temperatures, they start rusting. Okay, once the device starts rusting, when you try to use it, you cannot connect the terminals. Then there will be a bad contact, and then it doesn't work. Okay? That is what. And then another is the vibration. So whenever the device is subjected to excess shocks and all, there should be no disconnect and all. So it should survive those vibrations. Okay. So again, this one is the reliability information. Okay, you will learn at a later stage. I mean, have you are you aware of something called reliability in electronics? Heard that concept? Each device, like as a human being, as a human, what we have a what we are born and then we die one day. Okay, that's the birth and that, and then the time between that is our age of life or whatever. Similarly, an electronic component also has the same thing. Okay, the moment we start use it, it doesn't have an infinite life. Okay, it will fail at one time of time. So that is called as the mean time between failures. That is the lifetime of the component. Okay, and it is how much? 560K hours. So 560,000 hours. How many days? Calculate. 1 year is how many hours? Roughly. Hmm? How many hours? 1 year. If I 24, how much is it? Huh? Right. So how many 560,000 hours is how many years? Almost 7 years. Yeah. So this lifetime is in the electronic terms, in the reliability is called the total life. So this lifetime, what it is MTBF is stands for mean time between failures, and for the equipment it is called as a codal life. So a codal life of 7 years is a must in the industry. So whenever you have any equipment, or when you people when you tomorrow you come out as engineers and then design an equipment, the benchmark for that equipment is it should have a lifetime of 7 years, and that is called as a codal life. Okay, and then it varies with time. This 25 degree is this model, this 560K hours is at 25 degrees. So if your temperature increases, what happens? Hmm? Yeah. So the industrial benchmark or the engineering benchmark is for every 10 degree rise, this lifetime becomes half. Suppose say this is at 25 degrees, it is at 560K hours. So if I make it as 35 degrees, what will happen? Lifespan will become how much? Half of it. Yeah. So again another 10, it comes half, it comes half. So higher temperature, the life will be low. That's why why you keep all these in air conditioning and all this is the thing. So whenever you have a computer or you have a sensitive equipment, so what happens is as the temperature increases, its life comes down. So to avoid that, we control this temperature. Okay. Let's skip at this point. I don't think so you can understand. See this, like say, These are all safety standards or safety things where when you have these DC-DC converters, when they are subjected to certain say influences, like say you keep it in a magnetic field or you keep it in an electric field, they should not get influenced by it. They should not get affected by it. So all that will be, specified by EMC and EMC immunity and emission. Emission is it should not emit any harmful radiations. The immunity is if you keep it in a harmful environment, this should not get affected. So this is again there are certain things which is of course this is something related to reliability engineering. I don't think so it is relevant to you at this point of time. Okay. Now these DC-DC converters, they'll be having a lot of input and output protections. Okay. So what will happen is it has to work reliably. It should may not get affected because of certain input conditions and certain output conditions. How do they neutralize that? So one is if it beyond say earlier I showed you that it has got an input specified input range. Okay, it works between 9 to 36 or something. Similarly, what happens if it exceeds the voltage? Suppose say I give 9 to 36. Instead 36 volts, there is say some 50 volts or 60 volts that is coming. So what happens is you need to have a protection circuit which will not allow the voltage to cross beyond that. Like say the input might fluctuate, but you have a certain protection device which will not allow that excess voltage to appear at the input. So you'll be using those devices as called as the clamping devices. They will be either MOVs or transient TVS diodes. This diode, what happens is it will allow only the rated. It has got a rated voltage. Beyond that voltage, what it does, the excess voltage will shunt to the ground. So it will be holding that. It will limit the input to that value. Similarly, you have under voltage. So what happens is whenever we have the voltage going less than that. Suppose say earlier we have to got 9 to 36. If my input is less than 9, what I can do is see here this control circuit is there or this G is there. Okay. So if I connect a switch between these two, if I open this switch, this will start or stop operating. A generator that is detecting the input voltage. When I feel it is less than that, I can disconnect any of these pins. So this C, G or C. If I ground this pin, it will go off. If I open this G pin, the controller will not function. So the output will not be there, and it gets protected for that low voltage. Then inrush current. So what happens is, when have you studied what happens to the capacitor when you first connect it across a supply voltage? Hmm? The instant at t, if you are measuring it with respect to time, at t 0.1, what is going to be the condition of the capacitor? Hmm? What will happen? At t equal to 0.1, say t0, voltage is 0. T 0.1 voltage is there, what is going to be the condition of the capacitor? So the capacitor will be always at the initial condition is short circuit. From short circuit it goes to open circuit. So what happens is when you connect a source and then there is a high input capacitance, there will be what a virtual short appearing across the source, okay, input supply. Because of that, what will happen? It's going to draw high current. At that time, the input fuses or the supply is going. If the input source is not stiff, what will happen? Supply will start drooping, and then supply also gets affected. To prevent that, you need to have a limiter. Okay. So which doesn't prevent that. So initially, after few moments of time, the capacitor again attains that normal impedance, and then that short is removed. So you have a thermistors. What happens? What is the negative temperature coefficient resistor? What will happen? So initially it is going to have a high resistance. Okay, as the current passes through it, the resistance reduces. So in the cold condition, it will be a high resistance. So what whenever there is a initially the moment you switch it on, there will be a high resistance coming into the circuit, which will prevent the inrush there. The moment the power supply voltage builds up, then it's again certain current flowing in, and then it gets short. So it prevents that. So NTCs are used for preventing the inrush current. And then by chance during the operation, instead of see our DC is polarized, okay, there will be a plus and minus, okay. So if I connect it by see always we are prone to errors. If we connect it in reverse, what will happen? Supply will the equipment gets damaged. So we need to have a protection there whenever in the event of anything that is connected in reverse polarity, the fuse blows off. So if you connect a diode in reverse after the fuse, what will happen? There will be the diode will be forward biased for the reverse polarity, and then the fuse will be a short circuit, and then fuse blows. So here you use either a diode you can either use a MOSFET also. And then in case of if your supply draws, if your DC-DC converter draws more current than the specified, you need to have a circuit that opens. You use a fuse on that. And then there is any, say, unwanted high voltage for a small time that is coming onto the input level. Like say in case of lightning, or say there is a bad connection where this supply is going on and off, there will be a high transience on the input. Okay, you want to prevent that, you use devices called MOVs or metal oxide resistors to prevent that. Then for EMI you have got these filters. Then harmonic distortion you get the EFCs and all. At present, this is something out of your scope. And then this one. So here, what happens is this DC-DC converters internally have got a switching element. Okay. By chance, if that MOSFET or the transistor goes, the heat develops across it. Because it's overloaded or something. What happens is internally you need to check the temperature rise on that, and then in cases of excess temperature rise, you can switch it off. So you will be using some thermal sensors like thermistor, or you have a thermistor, and then you can switch it off by sensing the temperature. Okay, so you'll have the lower temperature protection. Okay, similarly, you have this is what we have seen for the input. The same thing, because this will be isolated. Sometimes there is no connection between input and output. So similarly, the output also should be get protected. So again, the same type of protections are available on the output also. This is one thing is the virtue of input affecting the device. The other one is load disturbs the output, and then that output gets affecting the DC-DC converter. So again, you have got protection devices for that also. It's a similar way, almost similar. Same devices will be there on both the sides. Okay, like over voltage, over current, short circuit, then thermal, under voltage protection. These are the same. This is one thing that you need to understand. Suppose say there is a DC-DC converter, okay, or for example, you would have seen in your bench supplies during your experiments in the lab, okay. They'll be, they have a specific rating, like say the supply is rated for 1 amp or something. You try connecting a 2 amps to that 1 amp supply. What happens? Hmm? Hmm? Fuse buzzer. Okay, right. Have you ever noticed behavior where the output voltage starts falling? As the current is increasing, the output voltage starts falling. So there is because there is a protection device inside there is called a crowbar. So what happens is as your current increases beyond a specified thing, to maintain the power constant, it will drop the voltage. So that's the protection mechanism that is built into the power supplies. So that sort of power supply that is called a load dump this thing. Okay. So this is all on the application side. Are you aware of DC grids? That's what a DC-DC converter. Okay, that's basically a device. Where that device gets used. Okay, this is a complicated this thing. I will just select a simple one. Okay, forget about DC grid. I'll explain something about solar panel. Photovoltaics. Are you aware of photovoltaics? Okay. See solar panel. When you see, I mean, you think solar panel, what it is? There will be a semiconductor on which a light falls on it, voltage develops, and it will be powering some load. Okay. It's not as simple as that. Okay. So this particular panel is made of number of cells. Okay. Okay. Each solar cell, what will be the voltage that will develop across a say the normal solar cell, semiconductor solar cell. So you have got two types of solar cells, the semiconductors. One is polycrystalline, other one is monocrystalline. So what will be? It's like a PN junction. Okay, when light falls on that PN junction, there will be some terminal voltage that is generated. What will be that voltage? Just a guess. Yeah. So there is going to be a zero point 0.6. Okay, zero point 0.6 voltage. Single cell will give you zero point 0.6 voltage. And what will be the power capacity of that? Hmm? So each cell, say, let's say a cm, a centimeter square of a solar cell is there. What can be, if suppose light falls on it, what will be the maximum current it can source? Hmm? The best efficient cell, which is around, say the efficiency around 20%, will give you something like 30 milliamps. Okay. So solar cell, where solar cell is a zero point 0.6 volt cell, a centimeter square of that cell is going to give you 30 milliamps. Imagine how many number of cells do you require in a 540 watt panel? So you require a large number of cells. Say this particular panel, okay. If you see here, you have got each one is a packed solar cell array. Okay. So here there are 144 modules which are connected. Each one of it is around 2 volts. Each module is 4 watt. Okay. Based on the area, say you have lot number of cells that are there. The each solar cell that is there. So here what it is you have got 24 modules in series and 6 cells in 6 modules in parallel. So it's all a combination of series parallel circuits. Again this 2 volt module again has got a zero point 0.6 volt cell in series and parallel. So that is how your solar panel is built. Got it? So there is lot of solar cells of each 0.6 volts or 0.5 to 0.6 volts kept in a series parallel condition to build this wattage. Like say all current adds up in parallel circuits, so there are lot of parallel circuits. Voltage builds up in series circuits, so lot of series modules that are connected. This is how the solar cell is there. Okay, solar panel is made. Okay, again in this solar panel, if you see, you have got this maximum voltage. Say if it is 540, you have got 48.92. When just a solar panel is exposed to a sunlight, Yeah.
connection of series and parallel.
Yeah.
So initial voltage is very small and current is also milliamps only. So what material they use for connection of series and
Copper strips. Copper strips.
Okay, copper only.
Pure copper strip. See, if you see it, you can see this. You can see these straight lines and these horizontal lines. They are all tinned copper strips. The pure copper is coated with lead. That is again, I
The
mean,
resistance would be very, very
yeah,
low.
yeah. So that's a thick copper strip that is there. That's why this is not done manually. You use robots for doing this because of so much series parallel complication. You have a mechanized assemblies that are doing this. So generally, these panels are assembled by robotic machines. For us, it just looks like a square thing that is there, which is giving us certain advantage. But it's a say complex arrangements of solar cells that are present on it. And at present, the efficiencies are something like 21%, 22, 23. Okay. So again, when this is open circuit, you have got a voltage of 48.92. All the cells voltage that is connected in series parallel, if you have a combinational effect, that is going to be 48.92. That is called VOC, V open circuit voltage. So each panel has got a V open circuit. Okay. Now there is certain maximum. Say if this panel is subjected to full intensity of light falls on it, then what happens is it will generate certain current. What is that maximum current is? It will be maximum current IMPP, that is called. When this, for this particular panel it is around 12.91. So 12.91 amps generates from that panel. When this much load is generated, the voltage across the panel is going to be 41.8. How much is the voltage drop between open circuit and load circuit? From 48 to 41. So something like 48.9 to 49. You take this 42, 7 volts drop is there. So the voltage fluctuates between no load to full load condition. There is a 7 volts fluctuation is there. And again, when there is no light to light, again the voltage fluctuates from 0 to how much? 0 to 49 volts. So the output of the solar panel will always starts fluctuating between 0 to 49 or 49 to, based on the load you connected, the 7 volts drop is going to be there. So now how do you use this? How do we use this? So this is the source what we have. Now we have to use this to power our loads. Okay, most of you have seen the solar panels are kept on the top of your house and then where you are harnessing the power. So how do you see? And then if we see it, when you see the characteristics of this panel, what will happen? The voltage starts fluctuating. So now once the voltage starts fluctuating, your output also will fluctuate. How do we use that? Hmm? So when this is starting to, when this sort of fluctuation is there with respect to light and with respect to load, what your DC-DC converter is doing? It will take a variable input and give you a constant output. So a DC-DC converter that is used for solar, you can use that thing again. The DC-DC converters that control the solar output, that is solar panel, the output is called as a MPPT converter. So what an MPPT converter is, maximum power point tracking is nothing but a regulation of this voltage. So from open zero dark, from the dark mode to the lighted mode, and from the no load to load, in between these points, the DC-DC converter adjusts the output to the maximum power point. That's why that regulator is named as MPPT. So basically, for solar, you use a DC-DC converter that is called as a MPPT tracker or MPPT regulator converter. Okay. So So generally a rooftop solar is like this. These are all the panels, okay. The symbol of the solar panel is that. Okay, here the solar inverter is what this. These are all the inputs of that DC converter, okay. So this is, we have connected how many? Around 15 panels in series. So like that, how many we have got? 8 panels in parallel, and that is getting connected to the, each one is a MPPT, each one is a DC-DC converter. Okay, so there are how many DC-DC converters in this? We have got 1, 2, 3, 4, 5, 6, 7. Okay, this has got 7. Okay, the 7 inputs are taken. Those, this is regulating the, so I mean the energy that is the solar energy that is coming out of the panels into voltage, that is connected to a inverter that is converts the DC to AC, and then that AC is used by a load. Okay, so this is how it is done. So this is, each input is a, I mean there will be lot of circuits. Say each one will be of 600 volts input, can amp around 6 watt of that. So this much energy is generated in that circuit. Okay, there are basically 2 inverters that are there. One is with 8 cells and another one is, see this one is with 8 cells, the other one is with 7 inverters, and then see this is, there are 2 systems, which one, this is, I mean the example I am just giving you, each one is generating around 510 units per day. Okay. So the total wattage of it is 56, the other one is 64, around 120 kilowatt of the system is there, which is generating around 510 units per day or roughly. So generally the thumb rule is, I mean anyone is aware of the, who is done something or basic of this photovoltaics. So 1 kilowatt panel will generate how much energy per day? 1 kilowatt solar panel. Any guess? Huh? No, this again depends on the solar radiation. Okay, from the based on the geography for Andhra Pradesh, or especially for say this Vijayawada Guntur region. So how much is the energy that you can harvest from this solar radiation? On an average, it is around 4 to 5. Let's say 1 kilowatt panel will be generating 4 times to 5 times, like 5 kilowatt hour, or around 4 to 5 kilowatt hour based on the season. On an average, it is around 4.5 to 5. So 1 kilowatt panel generates 5 kilowatt hour of energy. That's the benchmark of this solar. Okay. Now this is a rooftop application where a lot of DC-DC converters that are, like say what we have connected is, we have taken the solar input and then given to a DC-DC converter which is going to regulate, and that regulated output is given to a DC to AC inverter where we get a AC to use it. So here, if you see in this thing, basic of this thing is, basics of loss of energy conservation is, what is that? Energy is neither created, so it will be changing from one form to another. So what happens? We are using a DC-DC converter or a form of rectifier, or what is happening? We are changing the energy from one form to another. So what happens when there is a conversion? Generally, I mean, what is the engineer's interest in a conversion? Naturally, efficiency. So we will be always checking the, I mean, how much is wasted in the conversion. So what is the benchmark in power? I mean, as a power engineer, each conversion, how much does it amount to? So each conversion, say from AC to DC, user rectifier or whatever it is, approximately there is around 20% loss in the conversion. Okay. So suppose say you're using a laptop. Okay, let's say you're using a laptop. So you plug the whenever there is a battery is depleted, what will happen? You plug it to the AC source. Okay, what is happening? AC is getting converted to DC. Okay, and then what is happening when you plug it into the laptop? What is that? Again, the unregulated DC is converted to regulated DC inside. Okay, like say your laptop adapter must be having around 12 volt DC supply. But again, what are all the electronics in your laptop use? Must be the display uses 12 volts. CPU uses how much? What is the voltage the CPU in a laptop uses? What's the current this thing? Hmm? What's the VCC of the CPUs that are there in this laptop or in your mobile? Say you will be seeing when you're buying a mobile. My mobile uses Qualcomm processor. My mobile uses MediaTek processor. Okay, have you ever browsed and seen what is the VCC of that? So it uses around 1.6. So again, there are certain other, specific, say your codecs and all other application specific circuits which are going to use 3.3. There are certain amplifiers which in your laptop which are going to use 5. So all the input 12 voltage, 12 volts what you give have to get converted to the respective voltages. So there are a lot of conversions inside. So what is happening? Each conversion is consuming from the AC. You are going to convert it into this last mile is around 3 volts or something. 230 volts is getting converted in a laptop into how many 3-4 variants. One is from 230 and you are landing up with 1.6. From 230 you are landing into 3.3. From 230 you are landing into 5. From 230 to 12. So there are so many conversions. Each of them is going to waste 20% of the energy. If we can avoid those conversions, we can make a product which is efficient. That's what is this. That's what is called as a DC microgrid for home. What is there is, see the solar generates a DC, right? So if we can use that DC directly to power the appliances, what will happen? We are reducing a lot of number of conversions, thereby we can increase the efficiency. So here what we are using is basically we are using a switch mode regulator, MPPT regulator. So from the solar panel we give a DC and we get a regulated 24 volts DC supply. And then this 24 DC supply, see earlier if you had a ceiling fan, it was what was your earlier ceiling fan? Yeah. So induction motor. So what happens is you will have a line and neutral. Again, you to create a rotational magnetic effect. What you need to do is you have to have a delayed winding which you develop with a capacitor. Okay. So here in the BLDC, the technology which uses is a permanent magnet. There will be a permanent magnet motor which is energized. In a certain phase level with a switch to DC. Okay. This BLDC fan is basically a DC operating fan. Okay, what will happen is to keep it compatible with your existing power supply. They have done what they have done is they have converted. There is a converter inside the fan which converts the AC to DC. If you bypass the DC and then directly connect it to the AC grid, you will be saving around 40% power. Okay, and it can be directly driven from the solar. Okay. So that is one you will be saving 40% of the power for the fans which you are using in your house. Okay. The second one is now all the lights have come in become LED driven lights. Okay, LED is basically a DC powered semiconductor. Okay. So again there all the LEDs within a light are either connected in series parallel circuit. So to get the sufficient light, okay, suppose you take this light, you have a lot of LEDs connected in a series parallel way where the light builds up to give us the required illumination. Okay. So again there this is driven by a direct DC. So again what we are doing to power this, again we are taking the AC, we are converting it into DC, then DC is again regulated and given to the light rod. That is what we call as an LED driver. Okay. That again that LED driver, if we directly use this on the DC, you will be saving 25% of the power.
You are using all this DC distribution,
Yeah.
protection and all.
Yeah. No, it's not difficult. See, this is in certain countries it is available. Only the problem with this is, see, only the compatibility. Like say, already we will be using certain things on AC, right? If this is totally put on DC, this has been tried and it's been working well in African countries where still they don't have this power, where they are relying on the DC power grid. Like each of their house will be having a solar panel. They are not electrified. We are fortunate that we have electricity and all. There are certain parts of the world which still live in dark. So there, this is the solution that is working. And this actually, this case study, I mean, this was presented somewhere in 1975, I think. 1975, this, not 1975, sorry, 1985. Electrical engineer from Chennai, Chennai IIT has, presented this. And then he has gone, he was given the best innovation award for that year. Only thing, the problem why he has failed to make it, the concept was he has got the award for the concept, but why he has failed is at those times these things were not available. At that day, you didn't have a fan that was running on a, you didn't have a BLDC fan. Fan was always on a running on a this thing. So what he has done is he has used the DC-DC converter booster to, operate it on the booster and inverter. So all these things were, efficiencies were not as good as what this was shown. And then once these technologies were there, then this thing has become a reality. Now, in the other part of the world where they are not electrified homes and all, in the deserts and all, even in certain parts of Rajasthan in India, where in the desert, deep in the desert, where they don't have these grid connections, still this is working. So again, your TV, from the TV, the regular TV, which is the CRT TV earlier, it has come to LED TV. So again, there again the same thing. You don't require AC into it. What we are doing, we are taking AC, converting it, and feeding it with DC. If you remove that conversion, again you will be saving. So this is like, in the daytime, what happens is when there is excess energy that is put into the battery. Okay, during night time when this thing is not there, you will be converting it from the battery. Okay, that is how, you will be power. You will be using this. It is going to give you 24/7 this thing. So this is a model application where you can see, how the DC-DC converters are used in industry. See why these things have become a reality nowadays. Okay, so this is again the technology enablers for microgrid or these DC-DC converters. Is DC-DC converter as alone could not be a success. Okay, this was successful because of the other technologies built up. Say one is the LED lighting, because it is a DC driven, and then you have a DC source, and the DC-DC converter is a DC regulator which can power the LED lights. So thereby you are getting the efficiency. Okay, and here you have got MPPT controllers. Okay, I'll share you an example. Okay. Want to break? Is a break? You want to break for some time? Yeah. After that, I'll tell you what an how MPPT has really saved on this thing. I'll just show you an application. Right. You can break for some time.
Dear participants, let us have a break for the 5 minutes. Brief break.
Once this told that it's model it on application, and this model it because this tool means for so then this was supposed to be delivered by no, actually nothing is going to be whether it is there or not.
Yes, sir.
I will take care because I have and I was there travel చేయాలా లేదా అనేది that's why I was
ఫ్లెక్సిబుల్ గా ఉంటుంది సార్ షెడ్యూల్స్ ఎప్పుడైనా మోర్ అడ్వాన్స్ చేసుకోవచ్చు ఈ 1 వీక్ కంప్లీట్ చేయాలి ఓకే
I was back yesterday. I messaged him from the airport.
షెడ్యూల్ నాన్ అంటే మీకు అకాడమిక్ పర్సన్స్ తీసుకోవాలి అంటే ఐటీసీ ఐఐటీసీ తీసుకోవాలి ఇండస్ట్రీ కంప్లీట్గా చేసుకుంటారు ఇప్పుడే వాళ్ళు యాక్సెప్ట్ చేస్తారు రియల్
Actually, the rule for this thing is, suppose say you take this DC converter, especially in the TVs and all these things now the concept is like ASICs వచ్చేసి overall semiconductor ఏంటంటే there is like ecosystem is you have the domain knowledge, like domain knowledge in the sense you know the technology languages, you know the application, and you know the response of the application. Then you design a chip, then you put the firmware, and then make a engine that is called the computational engine. Suppose for example, energy. We have a chip that is got the speed, I think we got a controller, and then we have got a analog interface to it. Then there is a ADC into it. Then this ADC along with a process will give you the total power measurement information, the firmware inside which will process and give you all the computation. Then you get it as a digitized information. This total thing now the new concept is called a bare metal, or they call it as a built-in engine. So now the thing is who is clearing the fundamentals, and then who can convert this fundamental to an application, that the semiconductor company is giving as a total this thing where now the IoT is. So now it is all under data transmission and then the data confinement, data standards, interfaces, where it will be communicated via the different media of communication. The technology that is there. So now the thing is, once you are clear with the concept, the fundamentals of the thing, there is a lot of verification. Basically, the core is energy storage, inductive ఎలా energy storage, capacitive energy storage. It is only cannot do any problem analysis, cannot do any conversion. You BDS కానీ BDS అన్ని ఇది is like main use of DC converters. So if you don't understand how the energy is converted participate.
So we'll start the session of the brief break.
Here we just see how a MPPT, I mean DC-DC converter will really improve the efficiency of a solar. Okay, so this particular this thing is there in our factory. Okay, see here we have located the solar panels vertically. Okay, see actually every building there is see we keep all these panels for making the elevation. Okay, instead of making using some other material, what we thought is why don't we put a solar panel so that the elevation area of the building will be useful. This concept is generally widely used in Japan and it is called DIPV. It is called Building Integrated Photovoltaics. So what they do is, as a part of the green building, they want to use every particular space of the building. So here we have used this wall to generate certain energy. Okay. So we have instead of keeping it at an angle, see for our area, like say Vijayawada or whatever thing is, for the solar panel to generate some energy, it should be kept in a south facing, okay? Because sun originates in the east and then sets in the west. So at the if you orient your panel in southwest direction, the maximum time it will be exposed to the sun radiation. But here, instead of see there is one part in the west and one part in the east. Okay. So instead of keeping it at 15-degree oriented in the southwest direction, we have kept it vertical. So what happens is, in this direction, it generates only 50% of the energy what it's supposed to generate. But still, we are able to use this building wall area to generate the energy. So that was the thought process what we had in designing it. So here, what we have done is, so we have made a grid. Okay, what we have done is we have used the regular department power, and we have rectified it and made it into DC. Okay, our main intention was to have a DC source to directly run all the equipment on the DC without using any AC conversion. Okay, only we are doing one conversion. In case the solar DC is not available, we'll get the DC source from the grid. Okay, so we have got a three-phase rectifier. We are converting it into a three-phase DC source. This is also not regulated. Okay, it's just a instead of using a step down rectifier, what we have done is we have directly converted the 230 volts 3 phase. I mean, we have used the 3 phase AC to convert it into a DC, and then we have got a 230 volts DC here, okay, DC line. And then we have a as I told you, we have a group of panels on the east side, a group of panels on the east side, and a group of panels on the west side. So we have two circuits for each floor. We have segregated as a floor-wise circuit. So our building is having 5 floors. So we had five circuits. So here we have a set of panels aligned on the west, set of panels aligned on the east. This is again giving a total. We have got 6 panels of 24 volts or 30 volts each connected in series. So again we have a 230 volts, 230 volts DC grid over here. So this again is connected to this main supply, okay. And then in case power is not there, then solar is not there, we have a battery backup. So again we have a battery network. So we have got again a set of batteries, 230 volts battery bank. So again we have converted the DC to charge these batteries, each battery. So we have got a DC-DC converter from 230 volts to 12 volts DC converter. So we are having a series of around 17 batteries. So that again gives us the DC. So what happens is these are all connected in parallel, and we have got a DC bus. The priority is whenever there is a solar, so the first energy should go from the load should power from the solar. So how can we do that? We have used a natural principle telling that. So we maintain the solar at the highest potential. So what happens is energy flows from a higher potential difference to a lower this thing. So what we have done is we have maintained the solar at a higher voltage, then followed by the AC. So the rectifier voltage of this thing will be lesser than the solar voltage, and then followed by the battery. So the battery voltage will be less than that, less than the rectifier voltage. So this was the priority we have kept. Okay. So that what happens is always whatever energy that solar is giving will be powered by the load. In case we don't use the solar energy for powering the load, the same thing is put into the battery. Whenever there is this we have used to power our building. So whenever there is by virtue of a holiday or nobody is there in the office, what happens? The same energy is put into the battery, so that we can use it when there is no sun or when there is no grid. Okay. So this was the concept what we have used. Naturally, the sharing is done by the natural potential difference method. Okay. So this was the readings what we have got. So as per our calculation, the estimate should be how many we should get around 146 kilowatt hours per day. That is, we need to generate around 146 units from this particular installation based on the metrics what each panel is supposed to generate. So, but what it is generated after this, we have been connecting all this. If you see this, so this was we have logged all the data between for successive days within certain time interval, every time interval. This is, say if we take from around 10 o'clock, say 9 to 10, it gave solar is 354 watts, and then this is 354 watt hours, and then from the rectifier is 5384 watt hours. So most of the power is from the rectifier, because at 10 o'clock the sun is not that much because it's on the vertical orientation, it's not powering the panel. Okay. Similarly, we see that average so on an average we are able to generate around so there's something mistake is now. Yeah, it is 1000. Yeah, it's 1121. Around 1 kilowatt only be every hour, average hour during the Morning hours it was 1 kilowatt, and then the peak hours also it was around 1.5. There is not much big difference. And then on average we are able to generate around 1.284 on an average per hour. We were considering the peak and non-peak. We were able to generate around 1.2 kilowatt. So it's roughly around 1.2 units, what we call as the regular 1000 kilowatt hour. 1000 watt hour is 1 unit. So it's 1 kilowatt hour we are able to generate. So during the overall for the day, so this is total solar generation. Per day, we were able to generate per floor. Instead of this thing is total put together, it is 8 units and 8 units, 16 units. So we had around the 4 floors. So 4, 16, 64. What was it supposed to generate? It was supposed to generate 146. How much we have generated? 64. So we didn't even generate 50% of the estimated distance. Why? Here we haven't employed any regulation. Okay, this is basically what has happened was here we have just connected that series and we have taken that energy, and as I showed you there, the energy is fluctuating. So all the time, because of the natural, potential difference that is there, it's not. It is not giving any output, because naturally, when the potential difference of this is higher than this, naturally load is going from the going from the rectifier. So rectifier is a strong switch source, that is it's having more power. So whenever there is voltage, whenever I load this voltage will fall below this rectifier voltage. So naturally rectifier will be at a higher potential than the solar. So most of the time it is going and solar is getting unused. So what we have done is the same installation. The same installation, we have used the MPPT. We have used a DC-DC converter. Okay, the same panels we haven't changed any of the panels, and the same thing we have put to a DC-DC converter, and then DC converter I started using the converted regulated load. Okay, after doing this was the result. So I was able to get how much? There I was getting only 60 units or less than that. Per day I am getting around 86. So I am getting as high as 112. So it was because I have oriented in the vertical, it is going to give me half. So it's almost giving me what is the expected thing. Why it is giving me this thing is unused thing. This is only the solar energy. See, it is not on the other side. So if we have used the DC-DC converter, which is maintaining that as a constant, it is regulating that. What it is doing is, it is doing tracking the maximum power point. How does it do is, as I told you in the earlier case, what is happening? So when there is my solar energy is there, what is happening when I load it? The terminal voltage falls down, right? When there is not enough load for the solar to power, what happens? The terminal load falls down. So it's falling down to a level that is, that is lesser than the second source. So naturally, what happens? Second source powers it. So that is how it is happening there. Here, what it is doing is, this DC-DC converter, what it is doing is, it is tracking the input and output. Okay. So the moment it is measuring the input and output. Whenever based on the load, the output voltage falls. So what it does is, it will regulate the current. So instead of having a high current, what it does is, it will prevent the excessive current that is being drawn from the circuit. So when the current is drawn less, so the terminal voltage increases. This control is done with the switching element. So basically it will be checking the output, and based on the output it will be setting the input limits. There is a program that is being done there. That is what we call as the MPPT tracker algorithm. So to understand, to write that program, you need to understand the basics of this, how this is happening. Only then you can write the program. So what happens is, how do I change my switching frequency on and off timing based on the output? So I'll have to, each time I'll have to estimate what is my input, what is my output. Suppose say if I reduce my current regulation to if I reduce from 10 amps, if I reduce to 9 amps, automatically the terminal voltage will increase. So what is that value I need to reduce my current? So each time what is happening is, here what is happening is, for every time the terminal voltage of the current limit of the circuit is being changed, so that all the energy generated by the solar is being pumped into the load. That is what is your MPPT. So this is the usage of your DC-DC converters. Like say without DC-DC converter, what is happening? One instead of 146, whatever that was there, I was only generating around 60. With the use of this thing, what is the DC-DC converter, instead of 64, I am able to generate as high as 100, or my average itself is around 80-85. So that 25 is the efficiency I got because of the use of the DC-DC converter in the solar. So similarly, it will be that way. So that is the use of these regulators, DC-DC converters. Okay. And then this is the general information. You know how much each of the generation things costs around? Say your grid power, whichever is you are buying, I think all of us, on the current bill you choose the other. So how much are you being charged for 1 kilowatt hour? For your residential this thing? How much are you paying? See, being an engineer, at least learn these things. Okay. How much? Kilowatt or unit ఎంత కడుతున్నారు? How much? With all your true up charges and all. I think somewhere, all the slabs, telescopic slab and all for a normal, who is using around 400 to 500 units, I think you are paying up to 8 to 10 rupees, okay? 8 to 10 rupees you are paying indirectly. మీ అందరూ అన్ని చూస్తారు యూట్యూబ్లు వాట్సాప్లు అందరూ రోజు యూ షుడ్ గో అజిటేట్ హియర్ అండ్ దిస్ ఈ గవర్నమెంట్ కరెంట్ పెంచింది ఆ గవర్నమెంట్ తగ్గించింది ఎవ్రీథింగ్ ఇట్స్ వైరల్. You people are not understanding what is the being an engineer, you are not even understanding what is you're paying for the energy. తెలుసుకోండి. So these are all the things, that basic things which you are being an engineer, this is the what is the activity that is happening around your life. Okay, so it is roughly around 10 rupees we are paying. Okay, and then if you have a diesel, you have a generator in your house. People who are living in apartment complexes and all, they'll have a generator backup. Okay, you know how much the unit generated on the generator costs on the diesel generator. Okay, we are having a backup. Okay, current point వెంటనే వాచ్మెన్ జనరేటర్ వేయండి, ఒక నిమిషం లేట్ అయిన రూపం ఎంత అవుతుందో తెలుసా జనరేటర్ కాస్ట్ ఒక యూనిట్కి? Will be paying, see, this I given you as an industry. Okay, in industry we use a bigger, heavier capacity generators. That's why it is 40 to 45. If it is a lower, like say for apartment complexes and all, it's going to cost you to 50 to 60 rupees. Okay. See, imagine the amount. Why it is happening so much is, imagine the amount of the power that is being generated in the power generating stations, thermal or hydro power stations. Okay, that is where this why still everywhere. Which is the most efficient generation station? Which type of power? Thermal. Yeah. Nuclear, but it's only prone to hazards. Other than that, nuclear is the most efficient power. That's why Japanese use only nuclear power. And the solar, what is that on this today? Solar. See, 2 years back, each watt of solar panel used to cost around 200 rupees. Okay, that was the price. Okay, now with the, what's the program that's going on now? Not aware. See, there's a lot of advertisement. Our Prime Minister is advertising every house should have their own solar, so that why it is happening? ఎందుకు జరుగుతుంది అది? Why Prime Minister is canvassing for in the country for every house to have a solar? As an engineer, please tell me that. Huh? Think in the engineering background. ఎందుకు అంటున్నారు? Hmm? Green అని అరుస్తున్నారు ఎందుకు? Everybody is telling green energy, green this thing, that thing. Why? Green environment, green building, green energy. Hmm? See, we have fortunately ఎవరో కష్టపడింది మనం ఎంజాయ్ చేస్తారు. See, we are using every comfort. Say, I mean, it's hot outside. We switch on AC. For that, we are getting power. So, where the power is coming from? We are using up all the earth resources. Okay. So the resource, we are not conscious about that resource. So everybody, we are using energy as it is to generate that energy. All the natural resources are being used. Okay, we are exhausting. We are living on fossil fuels. Fossil fuels are one day going to get exhausted. Second thing is, we are converting the energy from one form to the other. The byproduct is heat. Okay, because of which the environment is getting, the temperatures are increasing, and their day is going to come minded. It is not that it's a signal ఏదో చూపిస్తున్నారు అన్నారు. Day, if you see every year on year, what are the ambient temperatures that are there? Freezing temperatures, the lowest is decreasing, the highest also is increasing. So if it goes this way, there is a day that is going to come where this earth is not going to be no longer a livable thing. We all, because the moment temperature crosses 50 degrees, we are not going to live, because no human body can work in an ambient which is at 50 degrees. There the people are 60 degrees, every one of us will vanish. Okay. So these are all the byproducts of fossil fuels. We are burning away the fossil fuels and then adding more and more contaminants to the atmosphere, which is not going to be a living thing. It's a livable environment. So thereby what happens is, if every house, if we start generating our energy, the total generation, that is the total requirement of energy, is going to decrease. That's going to make a big impact on the generation stations. Okay. So all that power cuts and all that demand, between demand and supply, is going to come down. So because of that, they are telling that use your energy, as well as because it's from the regular solar, you need not pay for it. It is on the free radiation that is there. So that's why they are promoting that. As on today, that solar is going to cost you around 15 rupees per kilowatt hour. Okay, and then the solar efficiency. So again, what is happening is, in rooftop, whatever we do, so we keep a rooftop, what will happen? We will be generating energy in the daytime, and then we don't use most of the energy in the daytime. So what we'll have to do? We'll have to put it in a battery. Okay. What type of batteries we use? Hmm? Hmm. So lead acid batteries. Again, what we are trying to do? We are taking one energy and putting it into a. So what we are doing? We are making electrical energy and putting it into a chemical form. So there is a conversion. Again, there is a loss. What is the efficiency of the lead acid battery? Hmm? It is hardly 60%. What's the life of a lead acid battery? Continuous use what a lead acid battery is around 1000 cycles, or say 1000 cycles is estimated to something like a 2-year life. So every 2 years you need to change your lead acid battery. I think most of the people who are having inverters in their home do that. 2 years or 2 seasons, so these days battery. The life of it is 2 years. Okay, and the efficiency is, you put 1 unit into the battery, you can take only 0.6. 0.4 is lost. 0.4 ఏం ఎలా లాస్ అవుతుంది? One is heat. So that heat is again ఏమవుతుంది? You are aware of it. బ్యాటరీలో వాటర్ పోస్తారా? ఎందుకు పోయారు? ఎందుకు డ్రైవ్ అవుతుంది? That's what. See, whatever is the electrolyte is there in the battery, okay? The heat is evaporating the electrolyte, and then you are again adding that. Only thing to add that to make it cooler, you will add water into it. So that whatever is that evaporation, latent energy that evaporates, that is a loss again to us. So that is there. I mean, if you say that's hardly around 60%. So why your mobile has become thin? మన మొబైల్ ఎందుకు ఇలా వచ్చినాయి? మొబైల్ రియాలిటీ ఎప్పుడైంది? అది ఎప్పుడు వచ్చింది? ఎప్పుడు వచ్చింది? Lithium was not straight away. When the mobile started, lead acid నుంచి లిథియం రావడానికి మధ్యలో చాలా టెక్నాలజీస్ వచ్చాయి. Anybody heard about nickel cadmium batteries? సో నికెల్ క్యాడ్మియం ఇవన్నీ వచ్చినాయి. వేర్ నికెల్ క్యాడ్మియం వీటన్నిటిలో ఏంటంటే weight per wattage per watt hour of storage energy is much less compared to your lead acid. That's the start of, I mean, having an alternative source of secondary cells. Okay. From there on, it started, and then what it has come, the final thing which has come is lithium battery. Lithium, there is lithium ion, and then before lithium ion, it was lithium iron phosphate. Okay, now most of the EVs use lithium iron phosphate, which is having around 90 to 95% efficiency. So from 60, we are storage energy wise, technology wise, we have traveled from 95. That's the reason why your mobile phones have become thick, or thin and all less weight. So with earlier, what was the, I mean, during early ages, what was the backup capacity of the mobiles? Any idea? Because everybody is using mobiles. Everybody, I think, buys their own mobile. The mobile వేరే కొనుక్కుంటారు కదా. ఫస్ట్ లో ఎంత ఉండేది? ఎనీ గెస్? First, earlier mobiles used to be around 350 milliampere hour. Okay, now what is the capacity you're getting? 6000 milliampere hour. That was the storage. Why this is happening is because of the efficiency of the materials, and other one is, the other benchmark is, what's the other benchmark? Weight per kilowatt hour of storage. That's the main driver why EVs have become a reality. Electric vehicles ఉంటాయి కదా. Electric vehicles లో ఏంటి? Internal combustion engine ఉంటుంది కదా. IC was dominating so many years because they could have done that with the lead acid batteries. Problem was, lead acid batteries తో చేస్తే vehicle efficient అవ్వదు. ఎందుకు అవ్వదు? Because for the size of the energy that required, the weight of the battery was the major component, and then so weight of the battery increases, the weight of the vehicle increases. Weight of the vehicle increases, the power to drive that always has to increase. So with respect to IC, internal combustion engine, that is using gasolines, this was the major drawback that was keeping the internal combustion engine much ahead of the EVs. The moment this lithium battery technology has come into picture, EVs have become a reality, because with less weight they could reach nearer to the internal combustion engine weight per kilowatt hour. Okay. Before we close, just I'm going to give you because since it was DC-DC converters in microgrids and EV, I'll just show you what a EV looks like. See this electric vehicle, if you see that, okay, the end thing which is driving the wheels in the electric vehicle is what? Which motor? Is it a AC motor or a DC motor? DC motor. See, your end thing that is driving the electric vehicle is an AC motor. Okay. So again, now to drive this motor, again, see the most efficient motor is a three-phase induction motor. So the main traction motor in the EV is still three-phase induction motor. So that again, to generate the three-phase, you require a high voltage bus. Generally in the EV, what is the bus voltage? DC bus voltage. Unlike your industrial engine, unlike your petrol engine or a diesel engine which uses a 12 volt battery, what is the battery voltage in the electric vehicle? It's around 200 to 250 volt battery you have inside. You have a HVDC bus. Okay. Here there'll be a high voltage battery on that. That battery gets charged with a onboard charger. Okay. And then here, what are the type of converters is the 200 volts. Do you mean to say that end motor also is 200 volt motor in your electric vehicle? What's the end voltage that is driving that motor? Hmm? Say this HVDC bus which is there, it is 750 volts DC bus. Okay, from 200 volts, it is getting converted to a 750 volt by a boost converter. There is a boost DC-DC converter in the jet that is again getting converted into a, then there is a three-phase inverter which converts that boost 750 volts DC to a three-phase that is driving your traction. Okay, so based on the how is the speed varying in the vehicle? Hmm? What technology I mean is employed in the doing that? Have you heard about motor drives? What a concept of VFDs, variable frequency drives. Okay, where the frequency is varied to vary the speed of the motor. Here also the same concept is used. The speed controller within a EV is again there. Okay, so basically what happens is you have a onboard battery. Then in case then there is a regular standby battery. Okay, in case the EV by main battery fails, there is a standby battery. That standby battery is again a 40 volt, 48 volts or a 24 volt battery. Again, in case of emergency, say where your main EV battery drains down, then this power from the local battery will get, it's for a short distance. Okay, short in case of emergency and all. In case where the main battery goes down, you have your all your control systems to work. There you have a low voltage battery, like your IC engines. Again, in case of short duration, that voltage is boosted to the, that is what is your auxiliary battery. That is again boosted to the high voltage, and the high voltage runs the motor. Okay. This is the main power unit. That's they call the power train. That is the main transmission unit of the electric vehicle is called as a power train. Okay, that is this particular motor, and then this three-phase inverter, and then this high voltage DC bus is called the power train. Okay, and you have got an onboard charger which converts the normal AC to the propulsion battery. That high voltage DC battery within the electric vehicle is called a propulsion battery, which is made of lithium iron phosphate or any lithium technology for example. This is where your Tesla and all are pioneering. Okay? And EV vehicle is full of sensors like a spider web. Okay? It's full of sensors because every particular function in the EV vehicle has got a sensor. All the sensory sensors work on 3.3 volts. Okay, so now your 200 volts or whatever 160 volts that is available in the EV has to be again converted to all these 3.3. So how is this done? So every sensory network has got its a local DC-DC converter where there is a main 200 volts that is converted into a bus voltage of 24 or 12. Then the 12 is again converted into the required 3.3. See, imagine how many sensors you have. Like whenever you people are riding your vehicles, all your mirror, all your infotainment system, and then what all your rear view camera, everything is having a DC-DC converter inside. Every module is having. So there's a huge lot of this thing, and then all your features like all your accelerometers, and then all your auto braking, everything is based on sensors. So all that sensory network is the digital signal, digital devices which are working on a low voltage. So the high voltage is again converted into low voltage to a multiple DC-DC converters. And mind you, in your electric EV, it is mandatory that every converter within that should have a efficiency above 95%. So imagine what is the technology they would have put in to have that minimum losses. Okay, again all the lighting. That's why all the electric vehicles are nowadays coming with the LED lighting, and all internal thing is all no longer the halogen lighting is there, because halogen is power intensive. Everything is converted into the DC lighting, because halogen again requires a driver to boost up the voltage. The entire infotainment system within a car is provided by this small tiny board, which is having all that thing. You mean to know about the infotainment system? All your music, all your LCDs, all your dashboard driven signals, everything is provided by this small board which is having a computer inside. This is the infotainment system. And even the air condition, which is again say in your regular IC engine, it is a mechanical driven this thing. See, this compressor is having a motor, it is driven by the engine mechanics. The engine, the compressor is driven by the mechanical energy. Whereas in an EV, this is substituted by again a AC motor. Okay, this is again having that high voltage AC motor inside. So again, there is a DC-DC converter which transfers from 200 to this 415 volts AC. There is a inverter, converter inverter. This is not. So I take last 5 minutes of the time. Okay. See, I just want you to tell. I mean, what all subjects you are knowing, and then how do you apply that to this application? Okay. Here we think that we are learning this and that. Where do we use it? Okay. Here, say there is a feedback network, right? Here I am sensing the output voltage, then giving a feedback signal to the controller, and this is going to control the energy that is being fed to the output. How do I model that? ఇక్కడ మోటార్ కనెక్ట్ చేస్తే ఈ బిహేవియర్ ఒక రకంగా ఉంటుంది. ఇక్కడ అదే స్విచ్ మోడ్ కంప్యూటర్ కనెక్ట్ చేశాను అనుకోండి, విచ్ ఇస్ బేసిక్లీ స్విచ్ మోడ్ సప్లై విచ్ ఇస్ కెపాసిటివ్ నేచర్. మోటార్ ఈజ్ ఇండక్టివ్ లోడ్. ఓకే, it behaves in one form. And then if I connect say a laptop, say it's basically a capacitive load, it forms in a different way. Now how do I make this circuit for a inductive load or a capacitive load? How do I design that for it? How can I model it? Here ఏమవుతుంది, ఇక్కడ నుంచి ఒక ఫీడ్బ్యాక్ సిగ్నల్ వెళ్ళి ఇక్కడ మెయిన్ కంట్రోల్ ఈక్వేషన్ మార్చుతుంది. what is the technology or what is that subject I use to identify that behavior? Hmm? Power electronics, no. Yeah, you're using control systems, okay? So you'll have to model this in a, there is a control loop, okay? So whether it is a single loop or a double loop, what type of loop I need to have, whether it is a proportional integral PID loop or it is whether I use a first order loop, second order loop. So all that thing, all that basic principle will be devising in this without understanding the control systems. You just cannot design this control loop to have a regulated output. Similarly, see here what I am telling you is I am giving a feedback signal, okay? That feedback signal is able to control this output, okay? So I need to have a device that is, I need to have a mechanism that is going to change my input output switching. So which subject I use then? Hmm? Our electronics is everything about this. But how do I determine that on time and off time? How do I solve that mathematically? Hmm? So you need to do your spectral analysis of that signal, and then you do the energy mapping. Then say each switch, how do I get that energy without? See, why I am telling you all this is until and unless you don't understand the mathematical model of an application, tomorrow when your real engineering career won't be able to do anything. Today, don't think that just solving a problem for examination is the issue. No. Whether you solve that or not, it doesn't make a big difference. Whether you get a 90 marks or you get a 35, it's not a big difference. But problem is, you know to apply that particular subject to a real-time problem. That is what is your engineering. That's it. Does your marks on the mark sheet is not going to determine your future. See, right now, why I am telling you that is because you people see, as compared to your earlier stage when I was doing my engineering, I never had a learning resource in my hand. Okay, so if I had to learn something, I need to go to a library and then search 100 books. Must be that book is available. That book might have it or might not have it. Okay, I don't even know what is an alternative source for this thing. But today, entire world is in your palm. Okay, mind you, you have got every resource in your hand. Okay, then you are able to you get every possible information related to everything. Okay, and then there are resources today which can break up the complex problem to the very simple solutions. Okay, if you really go browse and say how does this work or what is the physics behind this, there is a lot of data available. So please use that, and then your ultimate aim is how to apply my learning to a physical problem. That should be your target in learning. Okay. That was only the thing I wanted to say. Okay, right? Thank you for your patience hearing.
Participants, thank you for your patient listening, and I thank you, Dr. K. Balakrishna sir, for spending valuable time in spite of his busy schedule. We're closing the session today. Thank you.